All right, you guys, welcome to Projectile Motion. What we did was we took a look at a video on screen of this basketball shot, or I should say this half basketball shot, and watched it a few times and realized that this looks suspiciously like a motion map that we've been doing all year long. It's just obviously not in a straight line. So what I asked everybody to do is to get a ruler and to draw. Now I'm going to be freehanding this, so this may not be as straight as it will be when you do it with your ruler. But I said, take your ruler and go through the same spot of the ball with vertical lines. Yeah, I can tell I'm not real straight here. All right, for all of the different parts of the shot. And then you're going to do the same thing. We'll switch colors. Maybe that'll make it a little bit easier to see. But then we're going to do the same thing with horizontal. All right, we're going to try to go through all the same parts of the ball as best we can. All right, this is where it's going to get tricky. I'm going to cheat. But since I don't have a ruler, I think you'll forgive me for that. All right, and what we can see is that we've got a pattern, or we've got a couple of patterns here, really. All right, so if we look at what's going on from left to right, if we look what's going on this way, as poorly as I have drawn this, I think what you can see is that you have equal spacing. Between your lines. All right, and as you go this way, as the ball goes up, you'll see that the lines get closer together. And so I said, what does this tell us? If we have equal spacing and we figure that this strobe image was taken in equal increments of time, this would mean to me, here, from left to right, we are moving with a constant velocity. And if you look as the ball goes up and they're getting closer together and it's covering less distance in the same amount of time, the ball here is slowing down. Right? So this is our first look at a little bit of projectile motion where we have two different motions happening at the same exact time, which is kind of neat. So the next thing I said was, let's represent the ball in a free body diagram. I said, okay, let's do a free body diagram. And everybody comes up with this arrow here of FG. And let's make that a little bit more of a dot, and that's it. Now, if you consider what's going on here with our forces, we have unbalanced forces in the vertical direction, but you notice you don't have anything left to right. That's still the same thing as balanced forces. So let me summarize that. So we have unbalanced forces, particle model, just in case you're wondering that's for, in the up-down or the vertical. And we have balanced forces in the horizontal. So these are our two types of motions that we have going on. The second thing then that I asked everyone to do was to draw a velocity graph. And after a little bit of fidgeting, what we agreed was that we needed two. And so we looked at it in the horizontal, we looked at it in the vertical. Now, horizontal, that's going to be my equal spacing here. Constant velocity looks like this, just a flat line. If we're dealing with something that is getting slower, right? It starts off with a velocity and it's getting slower, or it's going towards zero, looks like that. Crosses the axis, and if we assume that it's going to come back down, we kept going and we just kept our line going. It's not supposed to have this little gap in here where the dot is, but you get the idea. All right, I think we're just not quite calibrated. So there we go. All right, so this was the beginning. This is the beginning of looking at what is happening with projectile motion. So the key things I wanted you to take away from here is that we have two different planes of motion and different things are happening. All right, we have no acceleration here, and we have a constant acceleration here based on our graph. Alrighty, so that's where we began. And then after that, I turned everything over to let's start with some practice problems. All right, so that's going to be our next thing. Okay, so then we all began with this on practice number 1. Yellow ceramic ball drop from rest from a height of 1.5 meters and decide what applies, figure out what's going on, solve for as many unknowns as you can. And off you went. So, alrighty. Oh, I thought I grabbed the one that I had with math in it. I guess I didn't. Ah, shoot. Hang on a moment. Okay, so what we've got here with the yellow ceramic ball, let's see, decide what miles apply and why. All right, well, I know that this ball is going to be falling down under the influence of gravity, which tells me I have an unbalanced force and a constant acceleration particle model. That would be my model. And if I wanted to draw some diagrams to go along with that, all right, a position time graph, velocity time graph, acceleration time graph. All right, well, if I have an acceleration, it's going to be a constant one because gravity is a constant acceleration, and it's going to be negative, so it'll be in the 4th quadrant. And I know the value of that is negative 9.81 meters per second squared. All right, that being said, I know that when it drops, let me change colors so this is a little easier to see. All right, I know that it's going to start at 0 velocity, and the slope of my line has to be negative, and it's getting faster. So again, here is my velocity time graph. My slope is negative 9.1 meters per second squared. It's dropped from a height of 1.5 meters. So the area under my curve is going to be how far it goes. And it is in the 4th quadrant, so it's got to be negative. You are ending up lower than you started, so that should be a negative displacement regardless. Okay, so that's what our velocity time graph would look like with the numbers in it. All right, now your position time graph, you'd be starting here, right? Because you're at a height of 1.5 meters. You're getting faster, and so you have an acceleration. That means that this graph is not going to be a straight line. It's going to be curved because we have an acceleration, and it's going to get steeper because we're getting faster. Now, where you stop that, I don't really care because we don't have enough information too much. You know, we don't have a ton of, I suppose we could go down to the 0, right? If we say that this is 1.5 meters, we could do that. All right, but it should be curved, and it should get steeper as you go. Okay, but this is the graph that we do our math with. So that's the one we're going to focus on, right? All right, so my initial velocity is 0. My time final is over here. And so we're working with our slope formula, which is our acceleration, right? Final minus initial, final minus initial always. My initial velocity is 0, my initial time is 0. So if I rearrange this, because we always make math mistakes when we have fractions, so we might as well get rid of the fraction, it's going to look like that in a straight line. All right, next one we're going to work with is our area under the curve, because we can't get any further. We're missing 2 variables here. So this is a triangle. So we're going to say the area under the curve is going to be 1/2 the base times the height. So negative 1.5 equals 1/2. The base here gets me to TF. The height drops me down to VF. Same 2 missing variables, so I have a system of equations. I'm going to take this and I'm going to put it right there because I'll substitute it out, and then I will be able to solve very quickly. So negative 1.5 equals 1/2 TF negative 9.81 TF. And I'm going to move up a little bit so we got some space here. Now, as for me, I'm going to get rid of my 1/2 by multiplying both sides by 2 to get that out of here. Otherwise, I'm dividing by 1/2. I'm not dividing by 2, I'm dividing by 1/2, so don't make that mistake. Negative 3, when I multiply 1/2, negative 1/2 by 2 equals negative 9.81 TF squared. TF squared equals, oh, I never did that part. Whoops. Equals something, some value. -3 minus negative divided by -9.81. And when I finish up in the calculator, I'm going to get 0.553 seconds. A couple key things here. This fourth quadrant being negative becomes really important because your slope is negative and you cannot take the square root of a negative value. And let's face it, we don't have anything called negative time. So watch your negatives so that you end up with a rational number. All right, next, let's resubstitute back TF. I would guess probably over here in this one and come up with VF. So when we do that, we're going to get a negative VF as well, but that's okay because it's getting faster in the negative direction, so that makes sense. All right, that negative doesn't mean it's slower, it just it's directional. So 0.553, and you get a VF of negative 5.42 meters per second. Okay. None of this is new. This is stuff we've done from the first semester. Okay, why is it a projectile though? Because the only force is gravity. The only acceleration is from the force of gravity. So that works. Now most of you, when you got started then on your next two problems, which are kind of squashed here down at the bottom, is it didn't take you very long to realize that the only difference is in the type of ball you're dealing with. This one's aluminum, this one's a ping pong ball, but you realize that everything else is the same. So you don't really have to redo the math. And it's a great reminder that mass does not matter when you're dropping something without air resistance. Okay, it's something we assume, but it's a really, really widely held misconception. You know, even though if you were to take a physics quiz from me, you would probably treat the problems the same. If you were looking at something out in the real world, you'd probably figure the heavier object would fall faster just because it's embedded in our, I swear, in our DNA. But it does not matter without air resistance, the mass. Okay, and 99.99% of what we do is without air resistance. So that works. So then you moved on to question 4, and things got a little bit harder. Okay, so let's take this one and draw a picture. Pictures always help. All right, so you've got a table, you've got a ball. It is rolling off the table horizontally at 3 meters per second. All right, the height of your table, 1.5 meters. And in class, we said, all right, so what is this going to look like when it rolls off the table? Is it just going to drop like the last problem? No, it's not. It's actually going to go parabolically, and it's going to form a half parabola. All right, these are called, by the way, horizontal projectiles, and there's some special stuff that goes along with them. We looked at a YouTube video from Khan Academy that was about 12 minutes long, but I didn't play the whole thing because they use a lot of just formulas and we use graphs. So if you do find that video, 8 minutes is all I wanted to show on there so you didn't get yourselves all mixed up. All right, so one of the things they did was definitely go through this diagram and explain some of the parts to it. All right, we do not know how far it goes this way. They called it D. I'm going to call it delta x because it's in the x direction. This would be what I would call delta y because it's upward. All right, it's up and down. Okay, but some of the key pieces to this, actually, let's go back. 3 meters per second. Notice the direction of my arrow because it's the velocity as it leaves the table. That's the horizontal velocity. And so if I were going to draw this as a vector diagram, if I was going to put arrows in everywhere, I would do all these arrows the same because as we saw from the initial basketball problem, this doesn't change. This part of the motion is the same throughout, and it's independent of the y. All right, so here at the very beginning, I don't have any y velocity, and that's where most folks make mistakes on this problem. All right, all horizontal projectiles, whether we're talking about balls rolling off of tables or bombs being dropped from an airplane or jumping off a cliff, as long as you're running horizontally, all that initial velocity is horizontal. It takes until you leave whatever's holding you up and you let gravity take over, and this one's going to be particularly long, right? That your y velocity is going to change. Your initial y velocity is 0. And that's really critical when you go to solve these problems and draw these graphs. So that's the most common error. Watch out for it. Now, verbal clues to know that this is the problem you're talking about. Look at this right here. See that? That's telling you that it's only horizontal. It's just rolling off of the table. You notice there's no angle given to you here. That tells you right away that there is no, it's a non-angled projectile, right? It's an angle of 0. So solve it this way. Some of the other key things, now we're going to do 2 velocity time graphs. You're going to do one for the x. You're going to do one for the y. Now, to be fair, if your initial velocity in the y is 0, it starts there. It gets faster thanks to gravity, right? Negative 9.81 meters per second squared. Right, it drops negative 1.5 meters. This is suspiciously like our problem from before. Okay, so that's going to be something we have to watch out for. They're obviously not all going to be like that. In this case, though, we do have something new, a horizontal velocity graph. And the 3 meters per second goes over here. Notice I didn't put it over here on the y graph because it's horizontal velocity, not vertical velocity. Okay, now the key to solving all of these problems is time. Let's face it, the time that it goes from left to right, this time, is equal to this time, the time it goes up to down. Right? They're not different. Time is not a vector, it's a scalar. So once you find the time for any of these problems using the one that gives you use the graph that gives you the most information. And this is the graph that gives you the most information. Start there, but find time, and then the time that you find here will be the same as the time there. And then you can just solve the problem pretty quickly or finish the problem pretty quickly. So to save space and a little bit of effort, let's face it, all of our numbers are identical to that first problem. So I'm going to assume if you cannot resolve this particular graph, you can rewind the tape or the video and go back, but you're going to get the time of 0.553 seconds. You're going to get the final velocity, negative 5.42 meters per second. And this time then goes over here. Now the main thing that is different is that you have also this area under the curve that you can find. And that is what we consider to be the range. This is a term that we use called the range. This, although it's really just sitting there, but anytime we're talking about the y, the other term that you will sometimes see is the altitude. All right. It's not spelled so well there, but I think you can figure it out. All right, so this one, keep in mind, you're dealing now with a rectangle instead. So if you want to know how far we go horizontally, it's just going to be the length times the width or the base times the height, however you want to say that. And it's going to be your 3 meters per second times your time of 0.553 seconds, and you will get, I want to say it's 1.6 something, so 1.66 meters. Okay, horizontal projectiles. Finally, the most complex problem of all. This is one where it's launched at an angle, and this requires, graphically, this requires a decent amount of work to figure it out. All right, let's start again though. Again, same idea, 1.5 meters, but now we're launching the ball at an angle. All right, and the angle they give you is a 20-degree angle. It's still 3 meters per second here. And again, you're trying to find absolutely everything that you can. All right, so some key differences here. The ball obviously is going to go up in a parabolic arc, and it's going to come down to the original height, and then it's going to keep on going down to here. Okay, that makes the problem tricky. If the problem just ended right here, it's actually easier if it came right back down to the same level. But we decided to jump the gun and make it really complicated and go all the way down to the ground. So keep in mind that there is an altitude here that we don't know. And there's also a total distance from top to bottom. And that's going to become important when we draw our graphs. Okay, so keep that in mind. But again, your velocity Changes in the y, but not in the horizontal direction. Keep that in mind as we go. Okay, so one of the key differences to solving this problem is you have to focus on the time of launch right there. That instant when the ball launches at 3 meters per second, it has two different components to the velocity. It has a horizontal component and it has an initial y component to that velocity. And that's really critical, that it's not the y velocity for the whole time, it's instantaneous. Okay, so don't be fooled. This triangle here that I just drew, this triangle is not a triangle like this. It's not the same thing. So now that I made a mess, let's see if I can erase it and get it out of there. All right, let's see if I can do that. And I'll just fix some of the stuff that I had. Right, I'll put my 20 back in there. All right, and I'll put my delta y. And then my other delta y went from there all the way to the bottom. Okay, right, they are not the same. I'm taking this initial point, this spot right here, and I'm exaggerating it in order to figure out my initial velocities. And this is where trig comes in. So if I want to use this, this is my adjacent side, my hypotenuse is the 3 meters per second, my opposite side is the VIY. So I'm going to go sine of, what was my angle? Oh, it was 20 degrees. So sine of 20 degrees, make sure you're in degrees, not radians, times 3 meters per second, and that's going to give me my initial y velocity. If I do the cosine of 20 times my 3 meters per second, that's going to give me Vx. So that's the first thing you absolutely have to do. And how do you know when to do that? When you see an angle in the question. So when you do this work, you get 1.02 meters per second for this guy, and you get 2.82 meters per second for this guy. That makes sense. The angle is small, right? It's below 45. You should have most of this in the horizontal. Okay, now we still need some graphs. So velocity graph for the x and velocity graph for the y. Vx is easy. It's always the same, isn't it? All right, now my value for Vx isn't the same as the last problem. So it's not 3, it's 2.82 meters per second. Again, I don't know what time final is yet, and I don't know what the range is. I don't know what delta x is yet, but that's okay. We can figure that out. The velocity graph is different. Okay, before our velocity was 0. Our velocity isn't 0. It's 1.02 meters per second. And let's face it, the ball is going to go up and reach this peak where it's stopped, turned around, and then it starts to come back down. So what that means is I'm going to go down to the x-axis. That's where the peak is. And then I come down, and I come down a lot more than I went up. See? See how that second triangle is so much bigger than the first triangle? That's going to be a different part of the problem. All right, this spot right here is critical because that's when velocity equals 0. Now, what time is that? Because let's face it, that's time on this axis. I don't know, but we'll figure it out. And then this is another time we don't know, but we can figure it out. And then this corresponds to VF, which again, we don't know, but we can figure that out. Now, what do we know? Because it seems like we don't know much. We do know the slope. It's still gravity, okay? And we also know that the 1.5 is somewhere in here. Now, let me clarify something. This triangle here is going to correspond to the first half of your parabola, right? Because that's where the velocity is 0. It goes to here. The second triangle, which is so much bigger, is from the peak all the way to the bottom. Now, you know that part of that bottom is 1.5. So honestly, I don't, I'm just going to eyeball this. Like, let's say, that's not too bad. It's kind of close. All right, that's the amount of this first triangle. It comes back down to the same height, right? And then it's got to keep on going. I know this is -1.5. This one, I don't know yet. All right, so again, we've got some stuff to figure out. But this is what your graphs should look like. And then we're ready to start doing some math. Okay, so the first thing you want to do, I think, is focus on this point right here. That's going to help you out. And there's going to be quite a bit here, so bear with me. I know we're going to have to go over to a second slide. But we're going to work with the first triangle. Now again, if it lands on the same spot that it launched from, you're going to have a little bow tie here. You're going to have two triangles that are equal, and the time will be nicely split in half. That's just not the case because we're going below that. So keep that in mind. This is about as hard as it can get. All right, so again, let's start with acceleration. That's our slope. Vf minus Vi, Tf minus Ti, negative 9.81. And our initial velocity, we know that. It's the final velocity that's going to be 0. So we're going to focus on this point as our final velocity, minus 1.02 over, we'll say time initial is 0, time final, we don't really know. What's kind of cool, though, is at least we can solve this one right away. Let's see. Looking at my spacing here. Tf equals negative 1.02, and we can just divide, and we get a final time of 0.104 seconds. So the time right here is 0.104 seconds. All right, that's helpful. That's helpful. If you know that this is 0.104 seconds, and you know that this is 1.02, now you can figure out the area of that triangle, and that will give you the height to the peak. That will give you the maximum altitude. All right, so I'm going to do, that's going to be the last thing I do on this screen, and then we'll move on to a new one. Okay, so that is a triangle, right, and that's what we're trying to find. .02, and that's some quick and easy math. Oh no, wait a minute. What did I do here? Let's just, oh, I just changed it from a full screen. That's all I did. Hang on a minute. All right, so now that we're back, let's figure that out. All right, 0.053 meters. Not too far. You know, what are you going to do? All right, so what I'm going to do is go to a new screen here, and I'll redraw my graph, so just bear with me, and we'll keep going. But we'll fill in some of this new stuff that we know. Right, give myself some more room here. 1.02 meters per second. All right, and that's going to be velocity of 0, time of 0.104 seconds, and then this turned out to be 0.053 meters. Oof, that's really hard to read. Sorry about that, guys. All right, now that means that this little bow tie piece is also 0.053 meters. And we know, well, it's negative because it's on the way down. Right? And this is negative 1.5 meters. That's actually quite handy. All right, we still don't know this time, and we still don't know this velocity at the bottom. All right, but we're getting, it won't take us too long. It's just going to take a little bit more calculating. Okay, so if we add this up, let's do that right away. Shall we? Let's see, total time seconds. All right, so negative 1.553 meters. All right, that's the total of the two triangles. It is negative. Make sure my negative's in there. So now we know the area of that triangle. Now it's time to figure out this one and this one so that we can then do the total time. And you've got two options here. I mean, technically, this one is 0, and this is the 0.104 right there. And then this is some unknown. And you can set it up for the base of this triangle to be the final time minus 0.014. And I wouldn't blame you if you did, except I'm going to tell you right now, you're going to get a quadratic equation. So if you want to avoid that, here is Mrs. Grady's trick to avoid that. Make a new axis right there and make that time 0. Just start over. Because you know the distance from here to here is 0.104, you can just add it back up later. And then you just have a regular old triangle to work with, and it's much simpler. So that's going to be what I do, because I like simple. Why not? Okay, so again, we still have a slope of negative 9.81. So let's start with our slope formula. All right, and again, we're going to start here as this green line is our axis. So VF minus VI, TF minus TI. All right, TI of 0, VI of 0 helps quite a bit. So I'm going to rearrange this all at the same step because we've seen this a few times already. So that's good. Now we're going to do this area of our triangle. Delta y equals 1/2 base times height, negative 1.53. 1/2 the base is here. Again, we're assuming that we started off again, so I'm just going to say TF. And then this is my height of VF. So let's see, I've got a little bit of this calculated out here so we can make it easier. 3.06 equals TFVF. All I did there was multiply both sides by 2 and get rid of it, or you can do the same thing by dividing by 1/2. It's identical, so up to you. And now I'm going to substitute. 6 equals, I'm going to put this right there. So I'll get negative 9.81 TF squared. This is stuff we have seen over and over again. So we'll divide by the negative 9.81, take a square root, and we get a final time of 0.563. And you can double check that math. Okay, now keep in mind, that's just this little segment right here. So now I've got this for the first segment and this for the second segment. So guess what? I'm adding those together. Let's do total time. 0.563 plus 0.104 seconds, and I'm going to get a total time of, oh dear, 0.666 seconds. All right. I want that. I can go back and then find the final velocity by, resubstituting here into this equation up here. And I think I did that someplace. Somewhere. Maybe I ran out of space. Who knows? But you get the drift, I hope. Let's go back to the horizontal one, though. Okay, back to our Vx that we left on the previous page. It looked rather like this. Okay, and I had 2.82 meters per second for my velocity. Now I've got 0.666 seconds, and I want to know the range. That's the area under the curve. So I'm going to do base times height, which is going to be these two values multiplied together. And 1.88 meters is the delta x. So a whole lot of things we figured out here. We figured out the maximum height, the total drop, figured out the total time in a few segments. A lot of steps, but it's actually not, the algebra is not that hard. You need the graphs to work out for you. And something to keep in mind, notice that this graph didn't change because the Vx graphs look the same in every single projectile problem. It doesn't even matter. All right, this one is what's different because we are starting with an initial velocity. So before, when we had a horizontal projectile, if you think about it, we had where this green line is. That's what our y graph looked like. If you launch at an angle, you have this extra piece that starts way up here and heads down. So that was our first few days. We took a few keynotes after that just to have some summary items of, tricks for vertical projectiles and for horizontal projectiles. Those I just went over like in the last 30 seconds. So hopefully you've gotten everything you need. All right, that'll do it.